Okay. Today's date is the 13th of January 2026. 13th of January 2026. The time now is 9:29 p.m. I was speech notes dictated already. WAV in it. Which is WAV. Let's look at the phone with card recording. Today's topic. Anything else I'm not using? No. Okay. So we're gonna do this properly. So we're gonna start with this. This is the folder directory I'm in. It won't really the folder, but this is I'm gonna open this because basically my repository OpenXS. I'm moving to OpenX computing because I can't post this because this is a ski sparse protocol, but it's a session for ref implementation because it's gonna be written in ref because it's a protocol. So it's get the downloader, they can give you feed, but if you're a valid member of the protocol. So it's like, that's the whole policy of the looking to deliver the best quality things ever. But this is literally the best of the venom. But, you got the demonized here, but, these are just code. If you want to file down, oh, it shows row one, surprise. So this is demonized as C. But this is this is some files in the repository which I want to upload it. So this is workspace end of November, workspace photos H of November, S for Sarah, I for India, G for golf, I for India, underscore, S for space, P for pause, E for alpha, R for Romeo, S for Sarah, E for echo, underscore protocol. This is screwing underscore sparse protocol. This is a human rights protocol. That's in Sigit pellet. So this repository is about the sparse missiles and things that are sparse, hence the sparse protocol. More specifically, I'm focusing on. Oh, this is not what I mean. I'm focusing on this. This I'm focusing on now. So basically, this is the video. We're gonna watch the video first. This is my videos. So this is for the share because you see the videos working. So this is what I do. I check the video. So the video is gonna continue here. So this is the video here. So this video is Mr. Obi Namdi is free and forevermore. So basically, this is my utopia, or what I expected to be my utopia when I was like a child. So I expected this to be a holographic interface. But this is focused on the filter and flash engine, what we call TMP. TPM. So this video, Mr. Obi Namdi and Mr. Heart and Soul Namdi is free and forever now because of the secret protocol. This is literally the digital world if you're gonna die. But the digital world is bound by MicroOS, so it's a metropolis because it's like a utopia in the digital. So you can upload yourself to the digital, and this is what the protocol sustains you in the digital. Because I don't want to put myself there without any way out. So this is the secret program, but it's not really about the holographic Muko Hollow system. It's about other things. So hello, the new one. So basically, this is it. So this is a. So we get terabytes per minute. This is it. So this is basically a filter. Filter. We go to noise stop. The noise stop is literally start. Basically, this is called 3-player chess. 3-player chess is me, you, and some adversary that I wants to aid us or help aid one of us in the worst case, in the best case, because I really can ruin everything together. So the adversary is an intervention, obviously, not in a secret program. So basically, in secret program, if someone is fighting, the adversary observes and acts on his own accord, but it shows that he's doing the thing for the right people, for his interest. So basically, it's 3-player chess. It's 3-player games, but 3-player chess is the best thing you can because chess is dynamic, but 3-player chess is the go-to for this kind of secret protocol, for real-world operation, or where humans are actively on the route in safety critical environments. So I would like to introduce you with the terabytes per minute. The terabytes per minute. Okay, the terabytes per minute is so you go to noise stop. The noise stop is basically basically it's based on lattice integration. So the lattice integration uses noise stop to start a boot sequence in series. So it starts and stop. So it's like it's just a boot sequence in series. William. This is a start processor. So the series implementation is literally you thinking of it like a cursor. This cursor can click here, and this will be an action, but this action has sub actions. And those can be like a left click and right click. You do other things as a hover. So the kind of start is on start, but it bubbles up to the source code, to the error, to the system, because it's a mosaic memory model. Because Micro OS, M for Mike, U for Black, K for Kilo, O for Oscar, -OS is a human rights operating system for the subatomic world. So the signal SEM is basically the terabyte per minute. The terabyte per minute is a module. It's a module. It has to be there in the firmware of policy. It has to be there forever and ever. Because the terabyte per minute clears noise that you are making in ahead of time, in time. For example, if you have a noise stop, once you're done with a noise stop, you have a noise stop, and that noise stop is what the terabyte per minute is declaring. It's like the explosion of it. So noise start is like, am I starting this in sequence? Am I starting this in sequence? The sequence is all you need to start it, but the thing that happens, something that's been started has to have a serious kind of a way. Because it's like I'm taking pulling a engine, pulling a generator. The generator starts when you pull it twice. So that's an aux start, but they have noise. So it's like is this really is this what I got? Have I got an auxiliary start? Is this how the engine is meant to work? Because the number is going around. The aux start is basically auxiliary start. So you have to start twice. But the noise is in series. And ends in sequence. So it matters how you start the system, because the system may be prone to noisy system and can be detected in real time. So basically, it's like for war zones. You don't you want basically for radio sequence systems. That so basically, I'm trying to have a relay system to look at what happens. So the auxiliary start works upon geometrical lattice. So it's like a FCZ, which are angular polar lattice angular systems, to determine what auxiliary constructions to use to boot or to load or to inject some artifact ahead of time. Because observing and consuming via probing. So again, processing is the act of the system. Not thinking isn't thing. Processing is the act of system. Observing and consuming and acting, observing and doing the job, observing and acting on the system without it's really again, it's a system that's non-deterministic, but it's in sequence or series, making it deterministic in the whole group. But system that's probe for solutions, and these solutions are active. So I was gonna say the kind of AVO3. So try. So this is a Nexus search. Basically, this is Nexus search. This is Nexus search. I hope it's here because I'm not just myself anymore. Now this is Nexus search. I've been introducing this for a long time, but this is an example of searching in Nexus search. This is Nexus search examples. Nexus search is a trident. It's a search engine that uses AVO tree balancing via characters. So, for example, in the you match it. It's a trinode, but uses the matrix to match characters. Because this is a field. This example. So, example here is not really the. This is not the best example I can give you. This one, let me give you an example. So this is my search index, searching version 1. Basically, this is not a good example to use, but it's in type. This one Nexus search uses. So it probes a solution based on a query already in place, but it has to rotate that query somehow. Because the term cat and fat and mat are different. For example, if you have the term Next search, N for November, E for Echo, S for X-ray, E for umbrella, S for Sarah, dash search, the terms keyword search. How this works? So next search works with the breadth-first search queue. So it works with basically tree node that, for example, if you search the word cat, mat, fat, and this is in a word bank. Do not think of them as database. Just think of it as a word bank, a word bank dictionary. So if I'm searching for the term mat, it extends a single protocol. A single protocol allows you to use 2 pointers to characters. 2 pointers to dimensions, life and work. At a time, life and breath and work for breath. But the Cisco model is just the so the Cisco of this will be C, right left node A, right node T, and then the M, right node left node A, and right node T, and to root F, right node A and T the right. So this is cat fat mat, and this is Cisco because it goes to root left right. This Cisco uses breadth first search and depth first search. So if I'm searching for term fat, the term let's say I'm searching for let me just put one mat. I can type in M asterisk, and this M asterisk I can type in asterisk AT to match everything. I can type in MAT, or I can type in M or then asterisk. But again, this is a good problem. So you can see, if the word bucket says it wants to keep the word ahead of time. So what this does is it is a queue to do this. So this is very important to understand. The word bank, cat, fat, mat, fat are just words in Israel, and vector search searches the word via matching, regular expression matching. Ref is the focus on. The goal of this is to have a series. Obviously, this is not a good example. This is the new one. This is the old one. This is no FS. This is the no file system one. But let's look at the documentation of it. So you can see caching. So this is next search, the MD. Let's see the usage. So this is a next search user. So it basically, this is very poor implementation of it because it's not polyglottic. But nested search is a function to match shared data via caching. So the cache is what's really important here because nested search cache is the go-to for the system. So basically this is a markdown file, but it's not really. So this is the API. So this API imports search engine. So it's a search engine. So it's new. So this is a Java file. So npm install at obnexus / computing /nexus search. We just download this clone this repository here. Which is github.com /obnexus/nexus search. npm install at obnexus/. Import search and import space right bracket space search engine space left bracket space search engine space right bracket from speech quote at obnexus computer/. Initialize the search engine. Const search engine equals new search engine. This is my search engines. The version and the fields are the schemas. So the field title, content, and tags are what the search fields are. So this search engine is the go-to for it. So the search engine has some kind of data. It doesn't glue. It has a clean separation of concern because of the zero trust principles from the data itself via the pointers. Because you discard the pointers. If you lose the pointers, you lose the data because you cannot anchor yourself to the AVO tree. So the kind of score, any kind of graph scoring, represents the pointer are this really the edges. Because the edges are auxiliary pointers. that you can clear at any time ahead of time. They are active, and active means they are not they know what they're doing. They observe and consume, observe and act. So this current search engine equals new search engine, and the name the key name called a my search engine version 1. The fields title, second are what are searchable. So await add document, await search engine to add documents. Array initialize square right letter of the array initialize right color by the title getting scholar content quick start for search engine type document and guide. And this is close brackets, close all engines, and this close result equals await search engine on search quick start. So the quick start is a keyword of the content here, the field title content, and the contents has this document can be an in-memory document, temporary, or a blob, or any kind of loadable artifact, which are called binary large objects that are searchable via the markdown file format, because the blob is a standard binary large info that dictates as dictated by the MIME type when loaded ahead of time. When with the system will continue. So the search main constructor of the search operation is Nexus Search. So in this kind of system, Nexus Search searches because it has connections to other nodes. So you can search, you can search in real time. I should run an example. Because this is the example. So the basic search implementation of this, come on, run this on computer later, but I have to put it in. It says so import search engine search option, search engine equals search engine, always search engine. The kind of it has fuzzy system. It has fuzzy matching. So the fuzzy matching is the regular expression that are a glob, which are glob wildcards. Basically the kind of wildcards you see when you match things on the terminal, because the terminal basically you have to type of wildcards. You have the wildcards for the globbing of the terminal, which is a good idea. Or you have the system kind of wildcard you see in the geometry regular expression, but they are bound by the schema defined, which defines the regular expression standard you're using. For example, if you're using the regular expression standard and using JavaScript, and you're using PEP 12, PEP 11, which is the Python regular expression, you have to adhere to the interface between the Python, if it's a Python interface, because if it's a web Python, basically it uses pattern matching to dictate how PEP via PEP, if using Python, to index a system within Java, because it represents what is in a web standard for kind of via middleware. The middleware is just kind of it's not middleware per se. It's just it matches better because it's a placeholder and template via the schema. So the configuration is there. This configuration here, so you can see this stop word. This is just this is not really good implementation of them, but this is just like Nexus Search is ready because it allows you to do bottom-up searching via, so you can match AATT many times on Wrok. So this is a matrix in the sense that it updates. Update the tree. If I have a longer word, say cat, I have the word cat, and I have the word catastrophe. Catastrophe, and I have the word mad, and I have the word, and I have the noun mate. Is mate a word? Mate. Impure products. Okay, mate is a word. Okay, so we have the word fat, and we have the word should I use the fast? I'm gonna put fat s, but that was like fat tests. Fats. We have the word fate, fastest. Okay, so I'll use the word fat. I'll have the word fastest. because just want to see and fat test, because the word fat have three words. So this is the same. So the kind of thing I'm saying is the protocol is resolving the kind of straw via problem. So it's thinking for you. So it can think for you. So that's right. So it thinks for you because you know you're here. So let's watch the video for a little bit. So it's like, the terabyte per minute is just called a TMP for sure. Because it's 1,000 kilobytes per 1 minute allocated for the time of 1 minute, so, at the local minimum. This is saying, so it reserves the memory ahead of time. And anything it uses, it can buffer for this, it can destroy stuff for this memory. Because this is what I'm saying. So the memory of the terabyte is 1,000 kilobytes, so not terabytes. 1,000 kilobytes for 1 minute at all times. So this is what the kilobytes per minute does. So this is called a KPM. Okay, so this KPM is approximately per second. A kilobyte contains 80,000 bits, base unit. A minute contains 60 seconds. And so basically, a kilobyte contains 80,000 bits, which is a base unit. A minute contains 60 seconds. 80 divided by 60 is 1 KB divided by the minimum is 1,000. So the bit rate of this exchange, which is called the bit rate. So this is called the bit rate, bits per second. You can have 133 bytes flow in 133.33 3 decimal places kilobytes per every 60 seconds. But 60 seconds is just calculated for 1 minute. So the idea of this is to have the probing system allocate this double. So we're gonna try to do this again. So 2 kilobytes is 80,000 bits divided by 1 second, and that will be so let's do 80,000 1600. 8 times 2, 16000 times divided by 60. 60 seconds. 160 divided by bits or 2 kilobytes. So basically, it's basically 80. So basically, 2 kilobytes divided by 60 seconds and convert it is 6,000 bits is 1 kilobyte, 2 kilobytes is 2,000 bits, and 60 seconds, I don't trust it, because it's annoying, because it's kind of hard to trust, So this is from kilobytes, from kilobytes 1600. So 2 kilobytes. 2 kilobytes is 2,000 bytes per second. So 2,000 bytes allocated for because 2,000 bytes is not enough. Yes, it's 1,000. 2,000 bytes is 2,000 bytes per second. SI definition, so the power. So this is 2,000 bytes. So the kind of bit rate of this will be, if everything presses once, if it's kind of entropy, so here's double the space for the time it's using, and that time is a second. So that would be double the space. It's not 100, because 100 is no. So it's sustainable because it's not a megabyte, it's a kilobyte. This kilobyte is 1,000 hours. So it works because it's a grounded in the system of calculating as a kilobyte second is go to hours. So the goal I'm saying to you is that the goal of the TMP is. The KMP, and I don't know what you and Unum, if using terabytes, is to allocate memory ahead of time and ensure that system artificial control system with token type token value, token type, which is the one token type, and token kind. So the kind of token kind, the token kind of the system replaces an as program. It takes the as the use of a system because it can be modeled as a system for a different purpose. It can be modeled one way but used for different purpose. And it has a one-to-one for a sparse use case. And if it is something, it can be used for that purpose in many contexts. Which is a context switch. So the kind of thing is token type, token kind, token value. Token type is a relationship, and token kind has a relationship too. That is a relationship to one or the whole relationship. So the kind of thing I'm saying is that this matters because of this video here. So the megabytes per second is 2000 divided by 60 seconds. So that'll be 20,000. Let me try to do it. 2000 divided by 60, which would be the 33.3 bit rate. But this has to be a system. So this would be, so if you do 60, this is like ADG to audio. This is like people with ADG. ADG puts it in type 1. I'm type 1. So I have to double the space, which is the 2000 kilobytes, half the time. And half the time to do it. So this would be, this is not good enough. So this is 2000, and half the time will be 30 seconds. So this would be 2000 divided by 30, because 30 seconds would be 66. So the also this would not be, this is like the unit of the bread. 66. 66. So the CM1 came. What is CM66? So 66 would be divided by 2. Basically 2. This is not complete. This is the kilobytes per second. So kilobyte, yeah, I mean kilobyte to BTS, from kilobytes to megabytes. So what I'm saying to you is this video is very important. Let's watch this video now. So this is CYMK. This one uses cyan, magenta, yellow key. The color key of the clock is what the mosaic system is. So the key to take the kind of because this can reduce to a system of RGB, but the RGB is for the color spectrum in the non-physical world, which is the digital world. So but the resolution is sparse. So in models, so you can see VR radiography in the still. So I'm saying to you, it works like this. So I'm watching the video. Let's watch the video now. So basically, I'm trying to get this right here. Yeah. So what is it? No, this is like you. Oh, so beautiful, guys. So you see this light in the room. This is my light one, my light bulb. But let's still at this house.
I'm so glad this is working as intended.
So that's like yellow, but I'm for this yellow. This is yellow now. Yellow, green, light. So I'm just seeing the colors here. These colors are green, but it's not coming out to the computer. The computer is not taking that green. It's still in it. It's not capturing because the color. It's just going to count for the color. The full color is green. There, I'm seeing green there, but it's like white. Because it's not looking there. So this is kind of problem with the space. Because if you're in a digital world, if you are far away, you start looking at simulation. Every time you simulate it, but this is happening here because you can't take information. And this is why the CYMK matters. No, I'm seeing blue. Blue? Is it blue then? Oh, this is light green, blue. This is blue, blue, sun blue. But it's a kind of color to it. Yeah. So I'm going to take this video frame by frame and process it. Because I'm saying I'm gonna do it properly. So yeah. So guys, it's so beautiful, guys. So it's not ready there. So even though it says confused, right? But this one is like kind of see what I'm saying? This kind of model here. But kind of try for myself. So I have double the video on autism, my video. But to the 4 years. So I love autism. So I love my autism. So it's oh my days. Oh my. I think it broke because it didn't break. So after the problem. So the idea of this is to use kind of color model to determine things in real life, because it's science, but the science is there and the science is real. Because I was using that bulb to glow and see what it glows, but In that room I was in, it was literally glowing red, green, blue, pink, purple. And not purple, wasn't going purple, but it was going kind of the hue of purple at some point in time. But I couldn't measure my eyes. Can you see where it was? Because I think it's like turquoise the same. Turquoise, yeah, it was turquoise, something close to turquoise. I don't know. I don't know. But it's basically like a holographic system that you take how kind of how much color is in the system, but this is a robot system, so that kind of bulb is not a bulb, it's like a lantern, but lantern for sleepers, so it glows color when the music changes, but outside it will look like there's nothing there, because it's really the pointer problem all over again with colors, and that's what I'm saying, if I'm seeing cyan and red, yellow, cyan and yellow, that means the color is red. In the simulation world, because red will mean you look at cyan and yellow at the same time, but it's a mixture of the color of red and so. So if I'm looking at yellow and alpha, we're seeing blue in the digital space. Blue is what the system measures, depending on the tools you're in. But you're taking a measurement of the system at all times, but it's blue because if you get on cyan, in the worst case, you can't get any more information than blue. And if you get magenta, and you choose the key, the key will give you yellow, magenta, you get red, green, blue, alpha, red, green, blue. And you get K, and you get alpha. This is just a little white. Then you get the contrast flip. Because it reminds me of an eyesight system. It reminds me because the problem is possible not to be modeled in that way. Because the World Bank is a different you can look up to. So in this one, those will be a color coding characters that remembers the state. Because it's basically based on Muko holographic system. It's basically meant to be holographic security provision. When you're in simulation, you now know you're in simulation because you're it's very for people in simulations. Modeling safely. So this is a tested machine. So. Say Malaysia Leo, yellow and then this color is black. The key color key is black, but this is based on the subtractive model because the key and you get white RGB white alpha based on the maximum color being used because this is basically there's an additive on color which is key is kilo. The key is what it takes to full system because it will not be a black because I just got to mix this over there. So that's very important to understand. What else, Danny? So we say this one. So what's so this is so TMP. The KMP uses a filter and a flash sequence. So a filter sequence, a filter and a flash. A flash is just an eureka moment. So you can have the system destroy something or store something instantly. Of course, like you can rebuild something, you can break it. If you can break something, you can rebuild it. If you can build if you can rebuild something, you can break it. If you can rebuild something, you can destroy it. If you can rebuild something, you can break it. If you can create something, you can destroy it. If you can create something, you can destroy it. Well, so I said it all at once. All of this is so short.
No, it's much better than actually being in outside. Let me start the video because it's better design studio constitution. And we are design web constitution.
So you see the color is beautiful. It's stopped now, but it's basically like science because it's basically a holographic interface. So the kind of system this is so beautiful because it's a quiet room, but the quiet room is like so this is a holographic room in the worst case scenario. It's like a boot sequence. So remember before I forget, it's basically a boot sequence into a holographic reality. Maybe it could be for mind upload. Okay, so it's basically for, I'm going to do, so it's for holographic room. Because holographic room, if this gets too real, you have to be actively monitor what's real or not. And, it's basically remove what is flash or not. Okay? So this kind of system is superior to holographic. It removes the necessary VR, it removes what's not needed. This kind of information is not needed because you need to measure what you need to process. Who you actively am. It doesn't matter where you are, where you have some kind of cool tech, in your hand. If it's not being used, you don't need to process it. That's why you enter that simulation. That's why you enter that emulation. So you're going to do something with that test. It's like it's basically a hotspot for heat and wave, and attract a lot of noise. In the system, and the system will then implode the cell into the outside. Before that, you have to stabilize the system because the system is holographic. Because it's really augmented reality, but it's not augmented. It's like a real reality, but with augmented construct. So it's AGI. So, like I said, the term catastrophe here was basically using Search was doing this again. So this was using to get a wildcat cat, and this cat, Matt's fact, will be searched via wildcat. Via the Rift ecosystem marker, the wildcard. So it will match wildcard, and the wildcard will dictate what word you pull out. But you take the wildcard, you take what you put in, because the wildcard already has a schema in place for you to say what the word is. What's a three-letter word? It's inverse Rift. It's inverse Rift. Because you're searching for sequence of instructions, you're searching for something via some kind of clearly orchestrated system that has a definite structure that won't break via some kind of schema defined. This reminds me of the GPRC, Google protocol for messaging. Because what's that protocol called? Messaging. But it's not. The GPRC protocol is the protocol for. For messages, but the messages are contracts, smart contracts. So this GPSC is like smart contract. This is a smart contract system because it doesn't force user into the contract. Systems doesn't say because it doesn't force user to pick a specific structure to look at. It just encourages user. It just kind of classes everything so you can find what they need. Because it's smart enough to give the next. So if the process types cat, types the word cat, it will obtain to catastrophe instead of math or fact. Instead of fastest, or because the term cat has already been decided via A*11 scoring. So the KMP is the shared 2 pointers to 2 directional pointers like K in and clustering via I hat, J hat, K hat, because this system was understand its own stress its own way, its own way. So it allows you to So I'm gonna download this. Hopefully now. So this is caching. So this is caching on MD. What's this caching do? So this cache. So you put cache manager, cache goes new cache. So this this usually use cache. The strategy is cache. So this is caching.mg on the Nexus search no our file system. This next time was a flexible cache. List with most of you. This is like 2 cache strategies you can use, but they cache the most used item. What you need to do is it's basically storing the most used query ahead of time, because that instruction path will be taken so many times, and those makes the system better. No matter how this person gets a food or water, this is basically how it works. No matter how people get a food or water, if it's a valid transaction, smart contract, it must be logged so more people can use that option authentically. It's an open new avenue, because the secret protocol is for survival, food and water, shelter, food, water, shelter. And the openness called constitutional framework. The constitution is where you live and you work. Where you live, breathe, and you work. An open framework is a policy. When you breathe, live, and you work, because work is optional. There's no point of fragmenting the constitution. It just works as intended. It doesn't fragment it. So the MRU is the most really caching. This is the caching structure, MRU. at runtime, because I saw the call running, it switches between runtime. It evicts the most usually used item, but it's an evicts the least used item, so I got it wrong. So it ensures that the system doesn't fragment itself in any way, shape, or form. Because it uses matching to match up and down. Basically, it matches using a Larian, a Cisco model. So if you have something that's matched once, the system confidence goes up, and that confidence is stamped, locked, and traced. So it opens up new avenues to make more so the command and control protocol can be more easier for humans to look to develop what is better. It's saying so. It matters to me. So this is a TTL, time to expire. Let's say. So, for example, we get count catch equals new cache manager 1001 1 minute TTL. Time to live. It's cache manager, and for stable cache data. 1,060 seconds. 60 seconds, so this is like a 1 hour. But the cache data is time to leave, so it leaves, it clears the data. So it matters, it clears it up. It's a weak data structure. It doesn't persist in memory because it's meant to be done. So, so you can prune out, cache to prune when they expire. So this example here. So it's basically giving you a dimension you can operate with life, work, and breath. Let's say this is an old one. Let's just see what this file is. No, this is basically a diagram, but this is the whole diagram, the whole diagram. So you see here. So I'm not sad. I'm not depressed. I am not angry. So it's really a system of so basically fixtures, examples. So these are the HTML examples. You can run npm run start. But this is a vanilla JS example, but this is a Vue.js. So the one that working at vanilla, common JS and React, the Vue is not working. Or wasn't updated. So this example is saying it caches the data. It's a file search service. It searches basically root paths. The goal of this is just having a blob, but this does work. This program does work. It finds the data and it does. I've tried it so many times. You have to just start the server with npm to do it now. This is not polyglotic as a policy. Using wildcard to detect how the system remains coherent over so this cache manager, this is a base document, IndexedDB. So it uses index database in Notebook 2. So index database. So this is your title. Cache manager 2. So this it works as intended. What else happening? So remember, it's a mosaic and it works as intended. Okay, thank you guys for watching. I'm gonna upload the video now.